Hi and welcome to my presentation on research into lunar masonry habitats using laser processed bricks. My name is Kevin Faris and I'm a member of the Lunar Construction Group here at the University of Adelaide. So what I'll do today is explain some of the reasons why masonry made from regolith is the logical construction material for the early stages of a lunar base. We'll look at selective laser melting, or SLM, as a means of doing this and discuss some of the advantages and disadvantages of this approach compared to other alternatives. And finally, I'll present the results of some preliminary trials that we've conducted at the University of Adelaide using SLM to produce small blocks. So I'm sure you're aware that the space agencies have plans to establish that lunar base in the next 10 to 20 years. The most likely location is at the lunar South Pole and possibly on the rim of the Shackleton crater. Initially, modular or deployable habitats will be shipped from Earth, but even with economies of scale as traffic to the Moon increases, it's likely that payload costs will be upward of $100,000 per kilogram. For the base to expand, there's a need for in-situ resources. Now, eventually we might be able to develop industrial scale production of steel, concrete and plastic on the Moon. However, our research is considering the early stage of base growth, where there's a need for simple, robust processes to make construction materials for habitats and civil structures like roads, landing pads and retaining systems. Now, the obvious choice for the raw material is lunar dust, or regolith as it's also known, and that's shown here. A range of processes have been proposed on how to turn lunar regolith into a construction material. One class of materials does this by adding a binder to the regolith. These include cement, concrete, geopolymer, sulfur and plastic bound regolith. However, bear in mind we're at the early stages of the lunar base development, so processed binders may need to be brought from Earth. Often the processes require water, which in the early stages of base development will be too valuable to be used in bulk for construction materials. And there's several issues with casting these types of materials in the lunar vacuum, as liquids are lost to vacuum before the material has time to cure properly. If the coefficient of thermal expansion of the binder and regolith fillers are different, studies report issues with durability under lunar temperature extremes, and sublimation can be an issue for low melting point binders during the hot lunar day. So what's the alternative? Well, sintering or melting regolith to make masonry needs only energy from the sun and lunar regolith, and you can turn that solar energy into electricity using solar panels. You can use a range of processes to produce sintered masonry units. The Lunar Construction Group will investigate several of these, though currently I'm focusing on additive manufacturing. The units could have forms similar to masonry used on Earth. To avoid the same issues that arise for the bound regolith, mortarless systems will work best. This means that the masonry has no tensile strength, so part of our future research will look at the potential for laser fusion to join the masonry units together, essentially welding the masonry units. Interlocking masonry, as I'm showing here, has obvious applications for road surfaces, earth retaining structures, landing pad and general dust control. In terms of lunar habitats, you can provide protection from radiation, meteor bombardment and extreme temperatures just by burying the habitat under compacted regolith. There's no need to waste time and energy processing it. However, atmospheric pressure at sea level on Earth could support up to 30 meters of compacted regolith on the Moon. You only need about 5. So pressurized habitats on the Moon, the main structural load will be tensile. And clearly, even with interlocking or welding, mortarless masonry is not suitable for carrying tensile loads and will not provide a hermetic seal. So one solution is to use an inflatable inner envelope imported from Earth with a masonry shell to protect it. So the masonry shell would protect that envelope and it mean that its weight could be minimized, so minimizing payloads from Earth. The other advantage is this shell would also support the overlying regolith if you lost atmospheric pressure within the habitat. And there's also the possibility of using SOMR, so the sintered or melted regolith, for internal non-structural elements. Okay, so let's move on to how we produce this regolith masonry. So selective laser melting essentially scans a laser over the surface of a regolith bed, as you can see here. So you then lower this build platform and raise a reservoir of powder and scrape some more powder over the top, and then repeat the process until you build up a three-dimensional shape. Now, as you'd expect, producing masonry in a furnace, particularly a solar furnace in the lunar context, would have a higher production rate. And previous trials also indicate you would be able to produce stronger materials. However, there are advantages of SLM block production. You can produce complex shapes without molds, and the shape of the units can be varied continuously. This opens up the possibility of parabolic or vaulted structures with interlocking mortarless units. The high energy and low processing speed can be compensated for by only partially melting the block, as shown on the slide here. So you print a shell and some internal webbing with raw compacted regolith in between. In effect, this produces a rigid reinforced sandbag. SLM have been undertaken previously, and I've provided details of papers by other authors in my paper. To date, most studies have used off-the-shelf printers with solid-state lasers, so that's diode or fibre lasers. The products have been small, of the order of a couple of centimetres, and strengths of the material have not often been reported, but when they have been, they've been pretty low, about 5 MPa. So the main point of difference of our trial compared to previous trials was the use of a Trotec CO2 laser cutter. We adapted the cutter so we could use it for SLM, and this is a very low-cost alternative to purchasing an off-the-shelf SLM printer. There are also advantages of this approach from a research point of view. So CO2 laser cutters have a longer wavelength than fibre or diode lasers, and so we wanted to see if the CO2 laser with greater penetration into the raw material would increase production rates. The cutter also has a much larger build platform than benchtop SLM printers, so we will be able to produce larger objects and can install modular equipment, for example, to create a vacuum within that space. At this stage, the process is manual, so we'll load some regolith into a little aluminium cup, we'll compress it with a manual press and place it into the cutter, melt the surface with the laser, and then repeat that process to build up our three-dimensional shape. Now, it sounds quite easy, but there are a lot of parameters to get right, and I've listed some of these on the slide. So to tune each, we go through 3 stages, which were also used in previous trials. And so first I'll produce a ring and change the laser power, scanning speed, and the spot size of the laser. And then we'll produce some tiles, and we'll look at the vector spacing and how to optimize that. And we optimized it for the mass and also for the flexural strength of these tiles. And finally, we'll start producing blocks, where we'll have a look at what vector pattern we should use, so how we scan across the shape, and also have a look at the lift thickness and what the optimum lift thickness is. So what did we find out? Well, essentially the CO2 laser allowed much greater layer thicknesses because it penetrated further into the regolith powder than previous trials which used fibre or diode lasers, and this might help scalability. The compressive strength was much higher than had been previously reported, though it appears that this higher strength comes at the cost of greater energy input, as you can see on these graphs here. So the more energy you input into the material using the laser, the higher the strength and the higher the density. But essentially we showed that the approach we were taking was a viable low-cost research approach to trial SLM printing. So just to sum up, so in this presentation we've discussed some of the reasons why SOMR mortarless interlocking masonry is a good choice for early lunar construction. It could be applied to a range of different facilities, and we've discussed some applications, one system where it could be applied to habitats. It describes some of the results of our low-cost SLM trial, which managed to produce high-strength material with greater lift thicknesses than previous trials, although the additional strength came at the cost of higher energy inputs. In future work, we're going to have a look at higher fidelity SLM trials using regolith simulants and possibly in a vacuum, and we're also going to have a look at laser fusion to join these masonry units together. And that's it from me. Please look at our paper for more details and get in touch if you'd like to learn more about our research. Thanks for your time.